Bismillahirrahmanirrahim. So welcome today for the second module of Abacus online learning. So today we will describe about the different type of the modeling technique. But however, I have a previous question from the last lecture about the different type of the dynamic analysis on Abacus. So dear student, we have two different type of dynamic analysis. The first one will be that that we have a structure, like we have some column or we have some wall, either RCC wall or the brick wall, and we are going to apply the cryptostatic cyclic loading, which is the uniform cyclic loading against each brick level. So that's mean that cyclic loading should be uniform. So we will apply 3 cycles of uniform deformations, and then we will perform this experiment. However, we have another type of dynamic analysis that will be time history analysis or real earthquake data. In that case, we do not have the uniform lateral load, uniform cyclic magnitude. So that's mean the shape of this one is like this. So you have some small value of the PGS, peak ground oscillation, then you have some higher value, and then you have some again small value, and then you have some higher values. So now you have to decide whether you have which type of the analysis you are interested to perform on your models. Mostly in literature review, if you are search out the word cyclic, they means cryptostatic cyclic loading, which I show you the previous one. So what that was, and we will discuss in more in detail. So this is the basic two difference among the this is the basic difference between the two dynamic analysis. Okay, Munib, and we will discuss more in detail when we will come into this section. Okay.
Okay, sir.
Now, before going towards the modeling technique, the first one I will like to share with you the most important tip. You can say the tip of the modeling or the technique of the modeling. We all know that in Abacus, if we are modeling the compressive strength of the concrete, the Pittel compressive strength in terms of the dynamic plasticity model, what we are doing, we have a straight line as marked by the red color, and then we have a non-uniform pattern as marked with the green color. In Abacus, we provided this portion with respect to E only. Okay, so you go to the dynamic plasticity model, you only put about the viscosity parameters. So if I'm going to show you the material property, concrete. So in this one, you are only define the density of the concrete and the elastic behavior of the concrete. And then in the elastic, you need only the Young modulus, which is the E, the slope of the line, or the stress divided by the strain, and the Poisson ratio. So by defining these two parameters, the density and the elasticity, you are going to tell the Abacus that your material, whether it is brick, whether it is concrete, whether it is a tile, that will be behaved in this elastic region in this manner. Okay. It will be equal to
yes, sir.
And for the non-linear behavior, you are going to use different techniques. You may have brittle cracking technique. You can use damage for the ductile metal. Normally, what we use plasticity, concrete damage plasticity model. So normally we use this technique as compared to the other techniques which is available in the Abacus module. So normally we use plasticity and then select the concrete damage plasticity. Now mostly most of them so among you 4 and 5 students, I think three students are working on the concrete behavior. So it's very important that when you are starting your modeling, only provide the elasticity and the density of the materials, and then just run the analysis And if your experimental curve, so I will draw a blue line. This is a black line, like a experimental load deflection curve of your specimen. So just provide the linear material properties of the concrete and try to run your analysis. And then plot your load deflection curve of abacus, which is marked as red, and the dotted line, the experimental. If these behavior, if your FEM behavior is following the path of your experimental behavior, that means you're on a right track. But if this is not on the right track, let's assume your experimental is orange and your FEM result is red one. So that means you have to play with your material properties. So this is one of the tip if you are working on some on some problem where you are using data from some other researchers from your previous literature review. You didn't perform experiment by yourself. Maybe he has some different material properties. He didn't mention all the required the information in the paper, and you have some confusion. So the only smart way is to just provide the linear one, because you know that the FEM need a lot of analysis time. But if you just model the linear part of the material, that will be very helpful for you in order to predict that whether your material will be going to adopt the same behavior as you are going to define it, whether your result will be very close to the experimental one or not. So this is one of the tips which I want to share with you, that whenever you start with a investigation on some other experimental work, and normally in Pakistan, due to the limited funding resources, we use this technique that we find some good literature review paper and we start just modeling on that one. So just model the linear one, and then you have to go towards the non-linear one. So I hope you can understand about this technique. Now, I will share these 3 and 4 different modeling technique in front of you. So this is the part of the one of the project which I did for my supervisor, and this is also one problem which last time yesterday a student asked me that how can sir we model the inclined members. So you can see that this is the girder, the pre-stressed girder, and it has a rectangular subject around externally, and internally we have some punches at the degree of 45 degree. So the only technique to model these things, I didn't use the different part. What I did it, if I show you the feature. So I started with the front. I try to, you know, so what I did, I just started the coordinate from this point, making a 0, 0, and try to coordinate all the points. And in the part technique, I just gave the exterior coordinates. I just model the 2D diagram in my abacus model, and then I know the length of the girder, and then I just provide the overall length of the girder. Now, how can I model the interior one? That's again very simple. If you in abacus, it is very understanding that if you have some, so let's have a look. I just try to model a new model. So we are using 3D deformable solid sphere for the concrete member. Okay. So just imagine that I'm going to, you know, have a polyline, connected line. I started my model. Then now this time I'm going to use some punches. Let's see, like this one, okay? So I make the exterior body and then I make the interior body. Now Abaqus automatically understand that this region where I'm just moving my cursor, that will be the solid one and that will be the hollow one. If I have another layer of the concrete inside it, I can again model it again. Or if I'm going to model our ducts, for example, sometime we have the problem that you have to model this small ducts. So I'm just also model this small, the ducts in the concrete. So I also model this one. Okay. Now I'm going to say okay, and then give the length of the concrete. Now you can see that we have this shape, and that shape is having like a hollow concrete girder, and also we have this ducts, small ducts inside here. Now, if you are going to investigate the pre-stress phenomena of the concrete, and you know that in the pre-stress, what we have the technique, we just make the steel cage. Then we have to insert PVC pipes, small plastic pipes inside it for the tendons, and then we insert the tendons in there. Then we just do the concreting, and then we just apply the pre-stressing on this on the structures. So that's if you're studying this behavior, then you need these small ducts inside the concrete member, and you will insert tendons inside it, and you are going to investigate the stresses which are applied on the tendons, pre-stress tendons, and towards the concrete, and how the behavior of the concrete region around this this tendons. So that's one of the modeling technique which you can maybe in the future you are going to deal with it. Now the problem with this thing, you have some hunches of the 45-degree, you have some circular member. Now when you are going to apply the meshing, that will be not very easy on this surface, because you cannot use the typical mesh area. So the first thing is assign mesh type, and that will be standard 3D. Don't use linear, use coordinate. And okay, now again here, please note this thing, that when are you going to calibrate your model? And I will also share my paper with you and also discuss more about the meshing technique. You can write more than 2 pages of your journal paper about different meshing technique available on the Abaqus. So first one, the linear and the hex. That's mean C3D8R, and that's mean 8-node linear brick. So the brick have 4 nodes at the top, 4 nodes at the bottom, so like a small brick, and all the meshing is like a small bricks. But if I select it in the linear, the wedge technique, that means 6-node linear triangular prisms. And then if I use the tetra, that's mean a 4-node linear tetrahedral. Now I'm going to select the coordinated. The most the most complex meshing is the quadratic hexa, which is C3D20, a 20-node quadratic brick. Wedge is a 15-node, and that quadratic has a 10. So this is the most complex mesh size or mesh type. You can also do the investigation in just a small beam. Just you pick a small beam of your ongoing research project, do the meshing of this type, try to find out the behavior of these things. So this is the mesh type. I'm not talking about the mesh size, which I already discussed in my papers. I'm just discussing about the mesh type, how the mesh type will affect the results of the FEM. And then the wedge, and then the TAT, and then the quadratic hex wedge TAT. So this is the most complex one. So I'm going to use this one for this my geometry. Then about the size, I'm just selecting 25. Now, 25 is very coarse size. And why coarse size? You can see that I have a very, irregular patterns around these things. The other patterns, they are very okay, but the 25, so that's mean I should need more finer coarse. So again, going to be here, apply 10, delete the previous mesh, say yes. The highlighted elements have been determined to have unusable quantity using simplified analysis. So that means I'm going to break my, my member around this region in order to get a good mesh. So that's the problem. Whenever you have a circular portion in a rectangular object, remember you're going to spend most of your time and this time in order to provide a good mesh. Now what the solution of these things? Just going to select the partition scales. Okay, the mesh will be going to reduce, no problem. And select the normal to edge. Okay. So this is the one partition. Done. That's the other partition. Now I'm going to divide one more time. Now let's see how this will behave, the meshing technique of our complex one. Okay, done. Now, at least we can solve the small thing. I'm going to also divide the circular from this side. Now let's have see the different behavior of meshing around this circle and the meshing around this circle, just for your understanding. Okay, the size will be the same, the type will be the same. You can see that we have now at least the regular patterns around this circle. If you're going to also divide a partition from this side of the circle, you have the similar patterns around the circle as compared to like this one, we have a very complex. And if I'm going to see a small brick to you, so this is the 20. So this is, you can find out 20 nodes of this point when you are going to measure 1, 2, 3, 4, 5, 6, 7, 8. So it's 8 sides. So that's how you can deal with the different type of shapes inside a different shape for the geometry purposes for your problems. Now another model which I want to show with you, I'm going to just save it for you. Corbels. Because yesterday one student asked me about how we can do the modeling of this technique. Sometimes you have this structure. So it's again a small beam column joint, but we are using it, we are applying the load on the beams as unlike, so for example, if you have a normal beam column joint, so in this case, the vertical member in this orientation will be the column and the horizontal will be the beam, and you are going to apply the load on this side. But sometimes you have an opposite approach. The vertical member is just for the resting, and you are going to apply the load on 2 loads on the top of the beams, and just you are going to investigate the behavior of the corbel. So that's one of the options. Remember, I'm using a point load. I'm not applying the area load or UDL load on the plate. So this is my point loads at the center. So I applied a point load at here. So that's why due to this point load, I'm going to divide my steel plate into the 4 plates, and respect to the steel plate thickness, I'm going to divide it. The concrete member, why I need to divide the concrete member respect to the steel plate, because I'm going to apply the tie assembly between the master and the slave, and for that the area should be same of the master and the slave, and that's the same reason for the other one. And at the bottom, I'm going to apply the support conditions in a line manner, not at the nodal point. So that's why I divided the bottom steel plate in only 2 categories, not in the 4, unlike what I did for my load steel plate conditions. Just let me discuss one more model with you, and then I will take your questions. Corbel and the circular column. Okay. That will be very easy, because again we have a small circular region, and in this circular region we have a circular opening. Yeah. So in this investigation, we have a circular columns, and in the circular column, we have the circular opening. But if I'm going to show you the assembly, we have a circular column, then we have a so we have this circular column, then we have a steel plate, and also we have around this circular column, we have this circular collar. And sometimes we need this circular collar or rectangular collar around the reinforced concrete members. And the reason is that we are going to apply the load at the top and the support at the bottom. And if we don't have this collar, the failure, all the stresses of the concrete will be conducted in this critical region. And we do not have a proper failure mechanism, which we are expecting that the column will be going to collapse at the middle side of the length. We have a failure around these edges. To avoid this thing, to reduce the impact of the direct loading at the top face or at the bottom face, we have to apply a collar. Also in this study, you can see a small rubber pad. So if I show you the rubber pad, this is a small rubber pad. We also apply this small rubber pad at the top of the column, between the column and the steel plate. And now what is the purpose of the rubber pad? I think in your lab, when you perform the compressive test of the concrete on the cylinder, you provide the smooth surface at the top of the cylinder by applying the sulfate mixed paste at the top and the bottom. So this is again that you are going to apply the providing a smooth surface at the top face of the load, so that when you are applying when you are going to apply the load, that load should be applying uniformly. If you have some different strata, variable contours at the top of the concrete cylinder or the column surface, then the load is not going to apply uniformly. So just to apply a smooth surface, in this experiment, the investigator applied the rubber pad on the top of the cylinder. This rubber pad is not carrying any stresses. It's the only purpose of the rubber pad is provide a smooth surface and transfer all the load on the concrete member at the same time. So that's the only purpose of this rubber pad. So these are different techniques. The last one is about that if you have a problem regarding the CFRP, regarding the how the rehabilitation problem, how you are going to apply the layer, the composite carbon fiber reinforced polymer layer around the concrete, or a steel jacketing around the concrete. So now then how can you apply these techniques? So I just selected one model. Just converting the old version to the new version. Just give me a minute. Again, in this one, we have our cylinders, and then we have a hollow sheets, and we just paste the hollow sheet of the CFRP sheets on the cylinders and try to investigate the behavior of the confinement of the on the concrete. So I did this experiment, the rehabilitation experiment during my master's back in 2009, 2010. And we do some retrofitting on the cylinders, also retrofitting on the bridge piers. So this is my concrete, and this is my concrete, solid concrete, and this is my CFRP. You can see this is the hollow one. And if I can show you in the assembly with respect to the section, so these are the FRP layers, and the center one is the cylinder. So we apply the load at the top and the bottom, with and without steel plate. I play with a lot with the different members. So just imagine you've been a structural engineer, you have a problem that you have a small bridge and the bridge pier is damaged due to the flooding or due to some collision of the truck to the bridge pier, and now you're going to rehabilitate, retrofitting that bridge pier either with the steel plates or either with the composite materials. Now you have the circular bridge piers. Normally we have the circular bridge piers due to their versatile nature of the eye around different X and Y during the seismic zoning. So we use the circular members instead of the rectangular one. And then you apply a steel jacketing, the hollow steel casing or the CFRP around it. So that's the problem. That's how you model your problem in the abacus. So I will share this model with you for your studies. So don't worry about the models. Now, if you have any questions regarding these models, regarding the geometry, regarding the meshing. Okay, now let's see the meshing of this thing. So that's the meshing of this. I use a normal 8 brick point mesh for the circular thing. So that's how you model different shapes in abacus. Remember, abacus is mostly used by more than the civil engineer, the mechanical people, the guys, they use abacus more than us. And they have a very complex geometry about the pins, the engines, the whole cars, and you can see beautiful videos on the YouTubes that how you, by using the abacus, you can model different complex geometries. So being a civil engineer, we are blessed. We do not have much complex geometries, and that's these are things maybe you will deal in your master's level or the bachelor level about the hollow column, the circular column, the retrofitting column, the pre-stressed girders, the tendons in the stress. These are the most complex geometry you are going to deal with. Now, if you have any question regarding the geometry, just raise your hand, and then we'll discuss about some cyclic behavior. Jiminy.
Sir, while creating hodges for pre-stressed girder, you said that we are creating it at 45 degrees. But you didn't mention any angle. तो सर आपको कैसे पता चला कि 45 डिग्री पे भी लाइन लग रही है?
Well, I use the meshing. If you see that I just use the meshing of the, I know that my graph paper is square blocks and I just draw a line between the member. But if you have a proper coordinates of all the geometry, you will just follow the coordinate, just enter the coordinates one by one. And I discuss how you have to enter the coordinate systems in my lecture 1, module 1. You can see, and beside, because I'm just trying to show you that we can define different shapes. So in just a limited time, I just randomly selected any angle. You can select 30-degree angle, 60-degree angle, depends upon your problem. But for any geometry, just mark the coordinates of the all the shapes, all the points, and just follow the coordinates. That will be, and now believe me, your life will be much easier.
Okay, sir. Thank you.
Umar, do you have any question? I think Umar is still in journey. Hamad, do you have any questions?
No, sir.
Okay. Now let's start the cyclic, the cyclic. So now I hope you understand the material point that only you will worry about the linear one, and then the modeling techniques. Now I'm going to apply this cyclic. Now before going to this one, I think the shape sent me last time the model. Shape models, and he has some problem with the meshing. So let's try to solve that problem, because the thing is that if we follow the step by step, that will be very easy for all of us. And yeah, material tool, shape model. I don't know why the problem with, okay, let's open cyclic. So this is the model which I prepared for the Osama. We discussed a lot about that cyclic, the quasi-static cyclic behavior on a column. Shoot. That was completely, yes. Do we have the result? Show you the result. No, I don't have the result right. Okay. Just imagine we have this paper for the cyclic behavior, confinement of reinforced concrete column with welded reinforcement grips. And remember, in the modeling, you do not need to model the real scenario. You only model the critical part of your member. For example, if I have to model this thing in my abacus, I'm not going to provide the strong base. I just start my column from 13-17 millimeter from this side where I'm just putting my cursor, and I just select the bottom face of this column as my fixed support. In real scenario, our investigator cannot use this technique because he needs a strong floor, small footing at the bottom of the column, so that if he going to apply the lateral loading at the top, the column will not slide down. So that's the reason. But for me, for us, the FM guy, I just model. So you should be a very smart. You don't need to apply the. You don't need to do the draw the whole geometry. You should be very smart person. So for example, in my case, I only model from this point to this point, and then I model my parts into the column in two parts. That will be the part one, the concrete column, and the steel plate or the hard concrete will be the part two. And I don't need to model the bottom one. So just imagine you are also dealing with some girder like okay, the example will be I will discuss the example in the next lecture, that you have some complex behavior and you don't need to model the whole thing. You just only model the B-spline. So in this one, I'm not going to discuss about the material, the methodology which he adopted. I'm just talking about that whenever you have a column or the beam column joint, you are worried about this hysteresis loops, and that loops are basically the percentage, the different percent, the drift level against the different drift level. The person, the researcher applied the loading. So just I'm just focusing on this cyclic loading, and the Excel sheet for this cyclic loading is. So this is basically the uniform cyclic loading, consistent cyclic loading on the column. And as I told you last time, that we have the total height of the column. What is the total height of the column? 1370 plus 2 from the base of the column to the center point of the load. So we have around 1650 millimeter total height of the member. So if you are going to take 1645 millimeter total height, so if I'm going to take the 5% of this total height, that will be the 0.5% of this total height will be 8.225 millimeter. And if I'm going to take 1%, that will be the 16.4, 32.2, 49, 4% is 65, 6% 82, 98, 8% is 131, and the 10% is 164. Now, how I'm going to apply this thing, that in the first cycle, I have only, okay, unfortunately, I don't have the actual experimental results. I just copied it from because the paper is published in 2000, in 1999. So I don't have the complete Excel data of this thing. Otherwise, I will show that in each these cycles, these loops are basically the response of different drift levels. It's not a one drift level. So if you can just monitor, this curve is passing from maybe 4% of drift level, that curve is passing from 2%, that one is passing from 1%, this small curve may be passing from 0.5%. Okay. So, and also he discussed about this thing that he applied loading. We discuss about lateral deformation, reversals consist of 3 full cycles at each deformation level, starting from 0.5%, 1%, 2%, 3%, etc. And for each drift level, how much cycles he conducted? 3 cycles. And let me know the one cycle. I told you last time, the one cycle is basically from 0 to positive to 0 to maximum negative to 0. So this is one cycle. So if you see in my diagram, you will see 1 cycle, 2 cycle, 3 cycle of 0.5%, 1, 2, 3 cycle of 1%, 1, 2, 3 cycle of 2%, 3%, 4%. So that's how we shape, we are going to apply this load on the member. Here I only plot one cycle of each drift level just in order to reduce the analysis time, because if my analysis, if I have some doubt that whether I'm applying the correct modeling or not, so that will be the problem. Now you can understand, maybe, so you can use this sheet. So the maximum applied lateral displacement is 50 millimeter. So 50 millimeter, and which is, if I just calculate the reversible calculation, so BG1, let's see the BG1 result. BG1 column. So this is BG1 column. So you can see the BG1 column is only up, don't have much drift level above the 3%, and we can find out that which is the maximum drift level where the BG1 is filled. So you can see the maximum displacement is 50 millimeter. You know the total height. You can divide the 50 millimeter by the total height into the 100. You will get the maximum drift level is 303%. Now we will see another column having the maximum drift level. Let's imagine BG10. So the BG10, the maximum displacement of BG10 is 76 millimeter. Okay. No, this is the spacing. Sorry, the maximum drift level. Okay. BG10. Yeah. So BG8. So BG8, the maximum displacement of BG10, BG8 is 100 millimeter. Okay. So this is the backbone curve. The backbone curve is when you're connecting all the maximum points of the loops, you will get this backbone curves. I have one paper of my own about this thing. I hope I will get an idea. 2015. Yeah, so these are different. Here you can see different cycles in different colors. So if I'm going to join the maximum point of these loops, the hysteresis loop, I'm going to take the backbone curve of my sample, and this is basically the backbone curve of my samples. Okay. Now the BG8 is 100 millimeter. Now if I have BG8, I'm going to just change it BG8 100 millimeter. That means obviously 6%. So I need to apply up to the 6%, cyclic loading. And how I calculate it? Now the time is a little bit critical. I can also change the time from 0 to 1 by using 0, 0.25, 0.5, 0.75, and 1. I can also use 0, 1, 2, 3 in order to complete the first cycle of 0.5%. So it's up to me. And how I use how I calculated the amplitude, that will be very easy. The 0.5% of the total height in positive sign, that will be the peak positive, then the 0, and then the negative, peak negative, and then the 0. So that's how the first cycle is completed. Now I have these results. I just copy paste all these results into my Excel, the Abaqus. I'm going to apply the amplitude. In amplitude, I'm using the tabular. Okay, now see the different options, available options for these tabs: tabular, equally spaced, periodic, modulated, decay. In decay, your lateral load is going to reduce. Actuators, you have a hydraulic actuator results from the lab. You recorded the hydraulic actuator movement, and you are just giving that movement to your abacus. And then the spectrum, which I discussed, that if you have a the data of real earthquake, you can also define the spectrum, the user. I'm doing the tabular one. So in tabular one, you need the time, the frequency, and the amplitude. You just copy the Excel data from here to this one, and in step. Now the total time, no, in the step time, and that's you define module 1. And then when you have the applied loading, okay, now we go to the load, the axial load. The axial load is applying on this point with the amplitude ramp amplitude 2. So I'm giving this amplitude here. If I have nothing, I just mention the ramp. This is the displacement. It's a concentrated load. No, this is the load, sorry. Cycle loading. So the cycle loading is applying on this one, -1 into amplitude. So I'm going to apply my displacement control load on this point respect to T20. I can also use here 1 value. I can also use here -1 in the reversible conditions. It's not a problem. And the main thing is about the amplitude. So you will run. Maybe you have some error due to your machine size, or the curves are not balanced respect to your experimental curve. Then you can change the time periods. You can ask to convert whole time between 0 to 1, and then all the steps. For example, here you have around 20 steps. So you can say 0, 1 divided by 20, 2 divided by 20, 3 divided by 20. In order to get 0 to 1, the amplitude will be same. So you can play with the time. You are going to tell the abacus that in 1 second you will apply the magnitude from this plus minus to this. If you are going to make 1 here, but if you are going to apply in this manner, in the order which I applied, that you are going to tell the abacus, okay, in 1 second of the time, 0 second means 0, 1 second means the first positive, 2 second means the 0, 3 means the first negative, and so on. So it depends upon the rate of the loading which the previous researchers applied. If the rate of the loading is very fast, you have to meet the fast rate of the loading. If the rate of loading is very small, step by step, you can say step by steps. Another option you can also try while defining the time span is a step time. In this one, I want to get the results against 1.85 like a step time. But in some time, I need the total time. So that means the total time of the spans. These are the two different options of the cyclic loading. So I'm going to share this sheet with you. Okay. Now, what I did in this one, I have 3 cycles of 3, 1. So these are the 3 cycles of 0.5%. Again, the 3 cycles of 1%, 3 cycles. So that's how I apply the load on this. I try to plot the curves of this thing. And this is the 1 cycles for each drift level, and then you can plot the loops. You can measure, you can replot the loops, FEM loops on the experimental loops, and the backbone curves of the experimental with the one. I will also share this Excel sheet with you, that model with you, and if you like that paper with you, so that you can just practice. Now, the last time one of the students asked me about, sir, how can we write the group journal paper? So this is the problem. Not many people, not many researchers conducted the FEM of these hysteresis loops. So if you can spare a good amount of time on these results and then apply the cyclic loading, and you have a very good correlation between your FEM results and the experimental results of the cyclic loading, that will be the novelty of the one. Mostly the people only give that curves, the backbone curves. So that's the only results, most of the researchers only conducted on this one, not only on the loops. So that's one of the weak, the gaps area where you can, apply your FEM knowledge. Now, let me know if you have any questions, so that we are just going to approach to the period time. Ji Umar.
Assalamualaikum, sir.
Ji Umar.
Sir, how to create this sheet, sir? Excel
That
sheet, sir.
will be very easy, Umar. That will be very easy. You have, okay. Okay, now you're going to give me a data, okay? Umar, what is the total length of your column?
1500, sir.
So I name it one cycle, one drift, okay? I'm not going to apply 3 cycles. So the height of your column is 1500, and the height to the top mid, that will be, let's take 300, okay? So this is basically your height of the column. Now, if your investigator told you that Umar started from 1%, you do not need to apply from this use data. So I'm going to name it as a use data. Again. So if someone asks you, okay, Umar, give me the response from 1%, so that's mean your 0 will be from 1% to 3%. So you are only discussing about this thing. Okay, Umar? Just forget about the everything. I'm just deleting this part. I'm just deleting the rest of the thing. Okay, just for your understanding. And if someone asks you, okay, Umar, please, can you give me the 1%? So that's mean your 1% will be started from 0, 0, and then 1, 2, 3, 4, 5, 6, so on. So that's only you need only to provide this data from one cycle of 1%, one cycle of 2%, one cycle of 3%, and your figure will be showing like this way. Now, if someone asks you, no, Umar, please give me 2 cycle of 1% and only 1 cycle of 2%. Okay, so I'm just changing the sheet here. I'm not changing, okay. We will use another graph.
Sir, this 1% is the magnitude of load applied at a time.
Now, this 1%, that means 1% of the total height, the drift level, the 1% of the total height of the column. So with the height, with the height of the specimen, you are choosing the rate of the lateral load. So that means your height is 1800 millimeter. The 1% of 1800 millimeters is 18 millimeters. So you are going to apply the displacement control analysis, cyclic analysis on your column. And in the first 1% cycle, you only apply 18 millimeter lateral drift like this one. So your column will be moving from this original point to 18 millimeter on that side.
Okay, sir, understood.
Okay. Now, if someone asks you, Umar, please give me 2 cycles of 1%, So that's mean so this is the 2 cycles of 1%. And then someone asks you, okay, only the 1 cycle of 2%. And then the 1 cycle of 3%. Okay, Umar? Now I'm going to change. You can see you applied 1 cycle, you applied 2 cycles of 1%, and then 1 cycle of 2%, and 1 cycle of 3%, and you'll come back to its original position. So your column. So how your column move from at 0.0 second, your column is at 0 in a state position. Then you apply 18 millimeter load positive in positive direction. Then your column will come back to its original position, and then minus 18 millimeters. So it's a push and pull analysis. And then again 0. So that's how your 1 cycle is completed. Then again 0 plus 18, 0 minus 18, then 0. Then 0 plus 36, 0 minus 36, 0. Plus 54, 0 minus 54, 0. So that's how you apply your lateral loading in a push and pull analysis of your on your column based on the height. Okay, now you can ask me, sir, how can I know that my column will bear that much of the load? And remember, we have the load deflection curve, so we apply the displacement and we calculated the load from the gauges. Now here in this paper, after applying the lateral loading, he also compare the experimental solid line is the experimental, and then the analytical results with the help of the equations. So this is the line with the help of the equations, I think the dashed line. So you can also you know about the American code that if you have the column having the compressive strength of this much, having the ties in this shape, having the rebar locations, the size of the area of the column with this one. So that column will be going to take with respect to this code, ACI code, you can also calculate, I think also given the equations. Yes. Summary of strength and drift respect to, so this is the experimental test column for resistance, and this is against from the ACI. Where are the table? He didn't give the equations. Okay, no worries. So you can also, if you have all these input data parameters about the dimensions of the column, the percentage of the longitudinal steel, the string spacing, the yield strength of the steel, you can also calculate your predicted load carrying capacity for each cycle or the maximum one. You can say, okay, if I apply 10 millimeter load, that's mean respect to ACI 318-95, my column will be going to behave in this manner. It will take that much load, and then you can plot the load deflection curve on your column. Okay.
Yes, sir.
So now you have the modeling technique. You have the cyclic technique. Now, today I'm going to give you one assignment, and you have to submit it on Team. I hope you know how to upload the assignment on the Teams. So just take this paper. So this is my paper. I will also share the Excel sheet of this paper. And try to model. I have these curves in Excel sheet, so you don't need to use. If you do not know the curves, you don't need. If you don't have the Excel sheet of this curve, you can also plot with the data plot. I discussed that also in my module 1. But I have these Excel sheets of these results. So what I'm going to say, I have how many models I have? I think 3 models. Yeah. So I have these 3 models. Control model with no FRP, damage model. We apply the load on the concrete model that's damaged, and then we apply the FRP, and then we have another model, other column, which is not damaged. So I'm going to give this paper, and now luckily I have 3 models and 3 students. So Omar, you're going to predict case 2. The geometry of all the geometry of these 3 models will be the same. I will also share the geometry model with you just to reduce your time. You understand the geometry, you understand. Okay, now this is one more thing. This is my whole experimental setup. I have the strong floor. I was very lucky. I performed this experiment in one of the best lab in the Pakistan in UAT Peshawar. I was so lucky that I got this opportunity. I was doing my master from Tesla, but I conducted all my experiment in the Peshawar. I was so lucky at that time. Thank to Allah Almighty. So I don't need to model all this thing in my abacus. I only model this portion in my abacus. This is the load, the artificial dead load. If I can show you, I have the real pictures. Do I have the real pictures? Yes. So these are the real pictures. So this is the load cells. I don't need to model this thing in abacus. It will only increase the analysis time. I know how much load, the magnitude of the load, it will be then 10 capacity. I apply the axial load. So I have the axial load, which is constant, which is not moving. And then I have that hydraulic actuator, which is moving. I don't need to model the base frame. This is no point. Okay. So Umar, you will going to investigate the phenomena of second, which is the difficult one, Umar. Munir, you're going to model the third, and Hamad, you're going to investigate the first one. So just have a read of this paper. I will share the Excel sheet of the data of the experiment one, and you have to, model all these 3 and then come back to me. Okay, sir, you have this experimental result. I try to run it, and my FEM results are like this one with the help of the cyclic loading. Okay, so this is one of the assignment.
Okay, sir, inshallah.
Okay, so
Okay,
just
sir.
take your time. I'm not strict about the assignment. You have maybe 1 week or 10 days to submit the assignments. Just model the geometry by yourself, do the parametric investigation, apply the calibrations. Let me know if you need anything else. So I will share this thing right now.
Sir, but we can't extract hysteresis curves from abacus.
Don't worry about it. I have in Excel for you. Don't worry about it. Okay.
Okay, sir.
Assignment. Now let me know if you have any other question regarding today's lecture, so that we will just close and we can just attend the pair.
Sir, I have a question, but not in this lecture, sir.
Okay. So try if you have anything for the next lecture. Okay, in the next time, if you complete this analysis, I'm going to, correlate your FEM results with the experimental one. Okay, I think I also have the model of this thing. I started it and then material. Jay Umar, do you have any question?
Sir, can I share my screen with you?
Okay. I'm going to stop the recording and then I'll take your question. Okay.
Okay, sir. Thank you.